So hydrogen is really unique. It's not like any other element. It's different from the elements in the same column because it's a non-metal and the others are metals. And so it's really its own thing. It really is much more attractive toward electrons than the other metals because it needs to make the same number of electrons as its noble gas. And so normally, how do we find hydrogen? Most stable hydrogen is going to be involved in a covalent bond with some other element. Often carbon, hydrogen form a good bond. Often oxygen, hydrogen make water, a very stable substance. So what's stable about the hydrogen here is it has a noble gas configuration and no formal charge. Right? That makes it stable. No imbalance in the charge. Sometimes you could see hydrogen with a +1. Not very common. A hydrogen with a +1 only lasts for a little while. As soon as a hydrogen with a +1, which has no electrons, comes in contact with anything that has electrons, it'll jump onto that pair of electrons and start sharing it. So there's water everywhere on Earth, unless you have a specific lab setting where there's no water involved. So when you have H+, it loves water. It just jumps onto a water. If you have an H+ and you have a water, what will happen is the water is fine and stable, no problem, but it does have a partial negative because it's polar. The hydrogen will come over here and jump on here and start sharing electrons with that oxygen so that it no longer has to be unbalanced. That creates a formal positive for the oxygen. But it's more stable than the hydrogen not even having a noble gas configuration. So at least the hydrogen gets a noble gas configuration by sharing there and making the same number of electrons as helium. And the oxygen still has H2, so it's okay. It's not very stable for the oxygen to have an imbalanced charge, but it's better. At least everything has a noble gas configuration. So that's how we normally see hydrogen sharing electrons. You can also get a hydride, which is a hydrogen that has a lone pair to itself. There's a full negative, and we said it's not very stable before because I've got 2 negatives and only 1 positive in the nucleus. That's a pretty big imbalance. The amount of negative is double the positive. It's really not a balanced ratio there between the negative and positive. So the small elements like that are even more unstable if they just have 1 extra negative or 1 extra positive because it creates a big imbalance in the positive to negative ratio. So this is really unstable. And if this comes in contact with anything that can help share those electrons and help to balance out that extra negative charge, this will start sharing electrons with almost anything that's willing to share. So a metal like calcium is not willing to share because it needs to be without those electrons to make its noble gas configuration. So if you have a metal hydride, that's unstable not because the metal is fine with the noble gas configuration with the plus charge, but because the hydride has this extra negative, it needs to share with something. So if that comes in contact with anything, even water that's relatively stable, the hydride will come in here and start to share electrons with the hydrogen. And the oxygen will grab its electrons back, and you'll make this. So now the hydrogen that was unstable with its imbalance in charge is now balanced. So when you have a hydride and water, you have hydrogen gas coming off of the reaction as bubbles out of the reaction. Right? Just like any reaction, though, it still requires a collision. So this hydride and the water still have to be moving around. They still have to collide because I still have to break this OH bond in order to get the new bond to form, and it always requires some energy in the form of a collision to start breaking bonds and rearranging things. So that's the basics of how hydrogen behaves. So some of the other elements we can group together because they have very similar behaviors. We can think, other than hydrogen, we can look at the other elements in group 1A. These metals, what do they all have in common? Well, they have 1 extra electron more than they need to make a noble gas configuration. Right? So their behavior is all pretty straightforward. They have a low ionization energy. It's easy for them to lose an electron. They're never found in nature as pure elements, meaning you're never going to find potassium, neutral potassium in nature because it's not stable. It needs to lose an electron to make a noble gas configuration. And since there's lots of things naturally around in the environment that can accept electrons You're never going to find a metal sitting around with that extra electron just sitting on it. It's always going to be pulled away by something that can attract it more. It's always going to lose that electron and make a noble gas configuration and take on a plus charge. Once it has a plus charge, then it's attracted to negatively charged things. So you'll see it involved in salts or ionic compounds. So that's how we see these metals. They also react with oxygen, right? Oxygen in the atmosphere, it can accept electrons. So if you have the metal in its pure metallic state with that extra electron intact, so you don't find that naturally, but you can get like a K plus, and you can force electrons onto it using electricity and make the K plus and do a neutral K. If you then take that and you have it in oxygen, you heat it up a little bit, that heat will allow for the collisions that are necessary. The oxygen from the atmosphere will come in and collide with that potassium with enough energy and grab its extra electron. And that then will become even more stable and it will release energy. So you see that light released when those elements get burned in the presence of oxygen because they react with oxygen. The oxygen from the air will take their electron. They also react with water. So if you have a potassium with that extra electron, you add water. The water will accept that electron. How does it accept the electron? It doesn't have anywhere to put it. Well, what has to happen is this OH bond has to break. So the OH bond is a pair of electrons. It has to break. So the oxygen attracts this new electron in, and then it has to lose an electron so it doesn't go above 8, so the hydrogen will take 1. So that will give me a K plus after the K loses an electron, an OH negative because the oxygen now has an extra electron to itself. 3 lone pairs and 1 bond gives it a negative formal charge, and a hydrogen with a single electron. So that's not very stable because the hydrogen doesn't have a noble gas configuration. So I've traded this broken noble gas configuration for this one. The advantage, though, is once 2 hydrogens, once this reaction happens more than once, and I do it again, and I get 2 hydrogens, well, then they can come together and form a molecule. So I see that hydrogen gas evolve from that reaction as the reaction progresses because these can come together and share and make a noble gas configuration. The potassiums cannot share and make a noble gas configuration. They have to give their electron away altogether to make a noble gas configuration. Right? So the metals in that row behave in a similar fashion. But we do know that as we go down the row, and this goes for all the trends we're going to talk about today, as we go down a row, there's more and more and more shielding, right? I have more and more layers of electrons. So those inside electrons, as I put more and more layers in, their negative charges repel the outside electrons more. So that affects their properties. So as in any of these rows, as we talk about, even over here in the nonmetals, if we get far enough to the bottom, we're dealing with a metal. Because even if it's close to a noble gas configuration, if I put so many layers of shielding in, the outer electrons are just not held in tightly because they're repelled by all that shielding and they just fall out and get attracted to other nonmetals. So they behave like a metal. But these ones especially, because they already can make a noble gas by losing 1 electron, and as I go to the bottom and they have so much shielding, they will lose electrons extremely readily. The elements in 2A are very, very similar. The difference in 2A is that these metals have a full subshell. So it's a little bit more difficult for them to lose an electron. Plus, as I go from like potassium to calcium, I'm adding 1 proton. So that 1 extra proton holds the electrons in a little bit more tightly. So they undergo the same types of reactions, just not as vigorously. It takes a little bit more energy to knock the electrons out of a metal in group 2A than in group 1A, because there's more protons. It takes a little bit more energy to do it. And then once the electron's knocked out and there's a new rearrangement of the electrons, it doesn't release quite as much energy. But they still, some of them will react with water or with acid to produce a hydrogen gas because they give those electrons away, and the hydrogen ends up picking those electrons up and ending up sharing with another hydrogen to make a covalent bond. So very similar to group 1A, just not quite as reactive. The group 3A elements, here group 3A is boron, aluminum, gallium, etc. Again, just like before, as we go down, we get more and more shielding, so they become more and more metallic, more and more easy to take their outer electrons off. And boron is a nonmetal, so boron is different from the others in that column because it is much smaller. With almost no shielding, it holds its electrons much more tightly. So it's going to be more involved in sharing electrons than giving them away to make a noble gas. But aluminum then is different because aluminum can give away exactly 3 electrons and make a noble gas, and since it has a bit more shielding, it's not too difficult for it to give those electrons away. And so when it gives electrons away, it'll form a +3 charge, and that can join with anions that have a negative charge. We can start to make ionic compounds. So we understand about that characteristic of metals. We've talked about that before. When you go down in that column, sometimes the metals will form a +1, sometimes a +3, right? So if I'm looking down that column, maybe like indium. Indium has a Kr core, and then a 5s2, 4d10, and then a 5p1. So that one electron in the p can be given away to form a +1 charge. So some of those metals will do that, and they'll exist like that. And then there's also 2 in the 5s, so it could also give those 2 away. But that's not going to make a noble gas configuration for it, because it still has these d electrons, right? So elements, once I get below aluminum to gallium, indium, thallium, those 3 are never going to make a noble gas configuration. So their ability to lose electrons is mostly due to the fact that they have so much shielding. So the outer p electron here, it can go away just because it's not held very tightly. And we can also lose the s electrons, but that d, that full d subshell is usually not going to be lost. Maintain that completely full subshell, the stability associated with that. The group 4A, moving one column over, now we're dealing with carbon and silicon as nonmetals, germanium, tin, lead, more metallic. Again, as we go down, it becomes more and more metallic, more and more easy to pull electrons away from the atom as we increase shielding. Carbon is really also a unique element. It is very special, and what makes it special is because it's small and it holds its electrons tightly, not as tightly as, say, nitrogen, oxygen, fluorine, but it's near the top. It doesn't have much shielding, so it holds its electrons tightly, but it's not super electronegative, so it doesn't grab electrons away from other atoms. So it's just right. It's right in that balance between an atom that holds its electrons tightly enough to make strong bonds, to make covalent bonds and share with other atoms and make those bonds strong, so we can make molecules like polymers and like DNA and other molecules where carbons bond to carbons that are important for the existence of life. It makes strong bonds because it holds the electrons in. It doesn't allow them to be pulled away too much. But it also doesn't pull the electrons away from other atoms too much. So it can share with a variety of atoms, and it can share an effective way, and it can make 4 bonds, so it can make interesting 3-dimensional structures out of these carbons when they bond together. It's really very good at forming a variety of compounds and making stable compounds as well, which is really important, because if you wanted to, in science fiction they talk about like silicon-based life form, because silicon's right below carbon, right? It should behave like carbon does. You should be able to make molecules that have silicon. The problem is silicon has a whole other layer of shielding. So when silicon starts sharing electrons with other atoms, they're not very close to the silicon's nucleus, and they're not very strong bonds. Other atoms will start to just leave and pull the electrons away from the silicon because it can't hold them in as tightly, because it's a little bit more metallic in character than the carbon. So carbon is really special. You can't really do with silicon what you can do with carbon. Silicon doesn't form a variety of stable bonds with a variety of elements. The bonds are a lot less stable because it doesn't hold the electrons as tightly. Once you go further down in that column, now you're very metallic, right? Because we keep adding more and more layers, more and more shielding. Those metals at the bottom, like lead, for example, it might exist with a +2. It has so much shielding, it can't hold its 2 electrons in that p subshell. It could lose them. The full d subshell is usually not going to be affected, but then there's 2 more electrons in the s, and those could be lost. So, for example, lead exists stable, often in nature, with a +4 charge. That's a pretty big charge imbalance. But when you have 82 positives and a +4 charge would mean 78 negatives, the ratio, 82 divided by 78, is still relatively close to 1. So even though I have a 4+ charge, it's still a relatively balanced ratio. And it just has so much shielding, those outer 4 electrons in the 6 energy level aren't really held in very tightly. N equals, in the 5A column, we've got nitrogen and phosphorus. So now as we continue to go over, we're getting closer to the noble gas. We're increasing the number of protons every column we go over, so they hold their electrons a little bit more tightly. So here we've got 2 elements in this column that are pretty much non-metals. They hold their electrons pretty tightly. So they're going to be able to share with other atoms to make the noble gas configuration, but those bonds will be pretty stable. They're not going to break those bonds up very readily. Especially when they bond with oxygen. Oxygen forms good covalent bonds, so we have phosphorus oxygen bonds, nitrogen oxygen bonds. There's lots of different compounds that involve nitrogen or phosphorus bonding with oxygen. So those are pretty common. And again, as you go down though, now we start to talk about arsenic, antimony. Those elements are more metallic because they have more shielding. Their electrons aren't held as tightly. So they're not likely to be found sharing electrons as much. And that's another biological example where phosphorus is found bonding with oxygen in the backbone of your DNA. That's what holds your DNA strand together. And there's a hypothesis that instead of phosphorus you might have arsenic. But again, because it has more shielding, it's not going to form bonds that are quite as strong. And DNA already is formed by relatively weak bonds. If you're looking at fossils, like old samples, and the idea that the whole Jurassic Park idea where you could get DNA from a mosquito and use that DNA to recreate something that's really, really old, DNA is not that stable. It breaks down over time. You're not going to find intact DNA inside of a really ancient thing because the phosphorus oxygen bonds are relatively strong, but they're not that strong. Over time, the vibration and light can come in and break those attractions, and collisions can occur. Even encased in amber, where there's not much motion, there's still enough motion for those bonds to break down. And so DNA is really not that stable over time. It's difficult to get long strands of DNA. So it will break up into tiny pieces, and scientists can kind of think about how to piece those pieces back together in a way that makes sense. But you don't have the intact DNA that they use for science fiction. So it's just the fiction part of the science fiction. Question?
Is that the same for frozen mammoths?
Yeah, so they don't have a full genome for those frozen mammoths because the DNA breaks down. So it's nice that it's frozen because at a lower temperature there's less motion, so it takes longer for the motion to cause those bonds to break down, but they still break down, and you have to kind of piece that together. You can get a sense for what the DNA should look like. You have some strands, but you don't have the full strand. In group 6A, now we're dealing with really more nonmetals. Selenium is not really that common in nature, but sulfur and oxygen are very common. They form bonds with one another and with other elements, so there's lots of different compounds that involve sulfur, lots of different compounds that involve oxygen, but the specifics of those we're not going to take a lot of time to get into. Same pattern though, as you go down, more shielding, so they become more metallic and less able to hold their electrons in tightly. In group 7A, we did a whole lab associated with these. These are the halogens. What we know about the halogens is they are one away from the noble gas. So they pick up electrons and hold the electrons very readily, so they're often found with a -1 charge. But they can also share electrons to make that noble gas configuration as well. So if I have a halogen where they're sharing electrons to make the noble gas configuration, they will usually react with hydrogen in the form of H2, and that will form HI in this example, or HCl or HBr, depending on which halogen you're working with. Generally, when a high electronegativity atom is sharing with another high electronegativity atom, both atoms are pulling on the electrons can't really get that close to either nucleus. So the electrons are not as stable as they would be if the higher electronegativity atom were sharing with the lower electronegativity atom, because then in that situation, the higher electronegativity atom can pull the electrons close, so they can get really close to its nucleus and form that attraction and become a little bit more stable. So when I say they form ionic salts, this is when the halogen forms a full negative and makes the noble gas configuration without sharing. That gives it a negative charge, so it will form a salt, which is an ionic compound. It'll join up with a metal positive charge to form an ionic bond. They don't exist as in their elemental form in nature, meaning in nature, if you had a halogen around, it would just eventually react by grabbing electrons from something else and becoming a halide with a full negative charge to make its noble gas configuration. They just have a good attraction for electrons compared to a lot of the other metals, so they end up picking up electrons that are floating around in nature and becoming negatively charged. Any questions about those? Okay, just a couple more here. We know the noble gases are relatively stable. For a long time, it was thought that the noble gases could never be involved in any reactions. No exchange of electrons, no sharing electrons, but I guess it's not too recent now, but not too long ago were the first compounds that involved some of the larger noble gases, right? So again, as we go down, as we get closer to the bottom, the larger ones have more shielding. So even though the noble gases are very stable, they have a stable number of electrons, they don't have a tendency to lose or gain electrons. When I have more and more layers of electrons, the outer electrons are not held as tightly. So other elements can come in and start to share those electrons, namely fluorine, because fluorine attracts electrons so well. If we put fluorine in a position where it didn't have enough electrons, and then we expose it to a noble gas, the fluorine that doesn't have enough to make its noble gas configuration will come in and start sharing with the noble gas. So the noble gases used to be called inert gases because they never were seen to form any compounds or undergo reactions, but now they're called noble gases because they can be involved in reactions and sharing electrons in certain cases when they have more shielding.